Welcome students. In this lecture, we are going to learn one of the different ways of generating frequency modulated wave. This method is named as indirect method of FM generation. Before looking into the concept, let us define what is a frequency modulated wave. We know that a frequency modulated wave is one in which the frequency of the carrier will be changed according to the instantaneous variations of the message signal. That is called frequency modulated wave. Likewise, if we define a phase modulated wave, we can define it as the phase of the carrier is changed according to the instantaneous variations of the message. So in frequency modulation, frequency of the carrier will be changed, and in phase modulation, the phase of the carrier is going to be changed. And these two properties of any signal, they are interrelated with each other. That is frequency and phase property. We can say that whenever there is a slight change in the frequency of the signal, directly, indirectly, the phase of the signal will also get changed. Likewise, if there is going to be some change in the phase of the signal directly, indirectly, the frequency of the signal will be changed. Okay. Now, since this method is called as indirect method of FM generation, we can say that indirect method of FM, that is indirect FM, is also called as direct PM. Because as I said now, whenever there is going to be some change in the phase, here we are going to change the phase directly. So whenever there is going to be some change in phase, indirectly, the frequency of the signal is also going to be changed. Okay. So this method is also called direct PM. And this indirect method of FM generation was proposed by E.M. Armstrong. So we can also name this method as Armstrong method. And in this method, we are going to make use of a phase modulated circuit. That is, directly we are going to change the phase of the signal, which in turn indirectly is going to change the frequency. So we are going to employ a phase modulated circuit, and it is otherwise called as direct phase modulation. And this FM signal is going to get generated from a phase modulated. So it is called FM is generated from PM. And in this indirect method of FM generation, we are going to generate a narrow band FM, that is NBFM, narrow band FM signal with low modulation index, with low bandwidth will be generated in the first stage, initial stage, and then its frequency range and modulation index will be increased at a later stage by using a sequence of multipliers, frequency multipliers. This is how we are going to generate a frequency modulated wave using this indirect method of FM generation. This is the complete block diagram that is used for indirect method of FM generation. If you closely observe this block diagram, this portion, this dotted portion, is meant for producing a phase modulated wave. So this block diagram, we can say this is a phase modulator which is going to produce a direct PM. Direct PM, which is nothing but indirect FM. And this indirect FM that is generated out of this phase modulator will be a narrow band FM. It is going to be a narrow band FM. So this first block is going to generate, is meant for generating a direct PM wave, or you can say a narrow band FM wave. And the block that is followed by this phase modulator, which is shown here, which is going to have some group of multipliers and mixers, where the frequency range of the signal that is generated out at the output of this phase modulator is going to be increased in sequence. See, we have not only employed only one group of multiplier, instead we have a sequence of multipliers where in each stage the frequency of the narrowband FM is going to get increased, and at the output of this multiplier circuits we are going to generate a wideband FM. This is what we have explained in the previous slide. That is, in the first stage we are going to generate narrowband FM by employing a phase modulator circuit, and in the later stage, that is in the second stage, we are going to generate a wideband FM by using a series of multipliers. Let's first look into the explanation of this phase modulator circuit. Now this is the block diagram of the phase modulator. As you can see here, there is a product modulator. We know that a product modulator is one which is otherwise called as balanced modulator. And the function of balanced modulator or a product modulator is to produce a DSB SC wave. That is, carrier will be suppressed and only two sidebands will be generated at the output of the product modulator. Okay. And the inputs to this product modulator should be a message signal as well as a carrier signal. These are the two inputs to the product modulator. For generating the carrier signal, we have employed a crystal oscillator. So from the crystal oscillator, carrier will be generated, and this carrier, with the help of this buffer, is 90 degree shifted in phase through this 90 degree phase shifter. And this 90 degree shifted carrier is given as one of the input to the product modulator. The other input to this product modulator is nothing but the message signal, right? So once this 90 degree shifted carrier and this message signal is applied to the product modulator, at the output of this product modulator, we are going to get only the sidebands. Okay, that will be lower sideband as well as upper sideband. Only two sidebands are generated at the output of this product modulator. And what is happening next is these two sidebands, that is upper sidebands and lower sidebands, are given as one of the inputs to the summer, and the other input to this summer is the same carrier which is generated by the crystal oscillator without any change in or shift in phase. So carrier directly through the buffer is given as one of the input to this summer, that is adder. The other input to this adder is the two sidebands that are generated at the output of this product modulator. Now this summer, what it does, it adds the carrier along with the two sidebands, and it is going to generate a PM wave. And this generation of this phase modulated wave will be explained clearly with the help of phasors at each and every stage. The stages are represented here as A, B, C, D, and E and F. With the help of each and every stage, that is phasors at each and every stage, we can easily understand the generation of PM wave. Now, if you look into this, A, B, and C, all these are nothing but carrier signal without any phase shift. That is, the carrier which is generated by the crystal oscillator is coming at this point A. The same carrier through buffer is reaching this point B. Likewise, the same carrier through this buffer is also been given to this summer. So this A, B, and C, we can name it as unmodulated carrier. So these are the phasors at each and every stage. So at A, B, C, we have unmodulated carrier without any change in phase shift, and this unmodulated carrier's phasor is drawn with a vertical line. Now at D what happens? At D, we are shifting the carrier in phase by 90 degree, and this 90 degree phase shifted carrier is reaching this point D. So the phasor at this point D is going to be a 90-degree shifted carrier, and this 90-degree shifted carrier will be represented as a horizontal line like this. This is unmodulated without any phase shift. If this is going to be shifted in phase by 90 degree, its corresponding phasor diagram will be like this, 90-degree shifted carrier. So far we have looked into the phasor representation at the points A, B, C and D. Next, E is nothing but this point. This is E. Okay. So at this point E, that is the output of product modulator, what you will get is, we are going to get only the sidebands. The carrier will be suppressed. We are going to get sidebands. That too both upper as well as lower sidebands. So at this point E, the resultant phasor diagram will be the phasor diagram of DSB SC wave, which shows lower sideband, upper sideband with some suppressed carrier. The resultant of this is obtained by adding these two phasors, and it is represented here. The resultant of the sideband is represented here. Okay, so at this point E, we have got only the sidebands USB and LSB. Now, let's move on to this point F. What happens at point F? Just two sidebands that are generated at E will be added with the carrier that is generated at this point C. So, E and C are added together and it will be produced at the output of the summer, which we have represented it as F. So, at F, E will be added with C. So, at F, this is also called as combining network because it is combining the sidebands along with the carriers. So, at F, we can say that the two sidebands are added with the unmodulated carrier because there is no phase shift here. Unmodulated carrier, how we have represented as a vertical line. Without any phase shift, we have represented the unmodulated carrier as a vertical line phasor. Now, this vertical line phasor will be added with the two sidebands that are generated here at the output of product modulator. So, together, upper sideband, lower sideband and this unmodulated carrier are added together. Now, for these three phasors, if we draw the resultant, this is going to be the resultant along with lower sideband, upper sideband and the unmodulated carrier. So, this is the resultant output that is resultant at the output of combining network. Now, we can indicate a phase angle phi at this point. This plays a vital role. Okay, is it clear? So, initially, we have represented the unmodulated carrier like this. Then there is going to be a 90-degree shifted carrier, which is represented as a horizontal line. And this 90-degree shifted carrier and modulating signal are applied to product modulator, at the output of which we are going to get only the sidebands. Phasors of the sidebands are represented at point E. Now, this phasors of sidebands combined with unmodulated carrier at point C is going to produce F, which is the output of combining network. And there we have introduced the phase angle phi. Now, this phase angle phi will be changed based on the amplitude of the sidebands. This phase phi is directly proportional to the amplitude of sidebands. Okay, whenever the amplitude of the sideband increases, the resultant is going to be quite slanting like this, and there is going to be an increase in the phase angle. So, the increase in the amplitude of the sidebands, that is the increase in the amplitude of the message, we can say, because the amplitude of the sideband is nothing but MA VC by 2. MA is the modulation index. It is always related with the amplitude of the message signal. So, whenever there is an increase in the amplitude of the message signal, we can say there is going to be a direct increase in the phase, resultant phase. That is what we have represented here. When amplitude increases, the phase angle phi increases. When amplitude of the message decreases, the phase angle phi will decrease. So, we can say that the phase of the carrier is changing directly according to the amplitude of the message. So, we are generating a direct phase modulated wave at the output of this phase modulator. This can be clearly explained with this diagram. Look here. Here, the amplitude of the sidebands are less. Amplitude is less. Whenever the amplitude is less, if we draw the resultant, if we combine the sideband with the unmodulated carrier and draw the resultant, we can see that this phase angle, the resultant phase angle is small. At the same time, whenever the amplitude of the sideband is getting increased, compare these two diagrams, the amplitude is slightly increased. Whenever the amplitude is increased, along with unmodulated carrier, if we draw the resultant and indicate the phase angle is slightly increased. So here the phase is increased. Is it clear? So we can say the phase is changed according to the instantaneous amplitude or variations of message. The phase of carrier is changed according to the instantaneous amplitude of the message. Right? And this is nothing but the phase modulated wave. So, if you look into the general block diagram, at the output of this first sequence of block, which we have named as phase modulator, we have generated a narrow band FM wave. The bandwidth of the wave that is generated here will be less. The frequency will also be less. And we are transforming this narrowband FM into a wideband FM by passing this signal through a sequence of multipliers. In 2 or 3 stages, we can increase the frequency by multiplying this NBFM's frequency with some other frequency generated by the crystal oscillator. Thereby, we can convert this narrowband FM into a wideband FM and we can transmit. And this entire method is called indirect method of FM because here we have not generated an FM wave by directly varying the property called frequency. Instead, here we have varied the phase property of the carrier directly. Only the phase angle is varied directly according to the instantaneous amplitude of the message. So this is called direct PM or indirect FM. Hope you have understood this. Thank you.